Hello, my name is Ashmit Pai, and today I'm presenting a paper called Contrastive World Models or CWM by Chayan Banerjee. The core idea is about teaching an AI agent to figure out what it can actually do before even it starts planning, and doing that better than current approaches. Let's move on to the research context. So the domain here is embodied AI agents operating inside text-based environments. The benchmark used throughout the paper is called Science World. Think of it as a simulation where an agent performs elementary science tasks like boiling water, growing plants, or mixing chemicals, entirely through natural language. The challenge, at every step, the agent sees a huge list of possible actions, and most of them look reasonable but are physically wrong. So let's move on to the critical bottleneck. Here's a core problem. Before an agent even thinks about what goal to pursue, it needs to answer a simpler question. Which of these actions can I physically do right now? Without that filter, the agent wastes steps trying impossible things, risk irreversible mistakes, and burns reasoning capacity recovering from its own errors. This pre-planning feasibility check is what paper calls the critical bottleneck. The current go-to situation is supervised fine-tuning, or SFT. You train a model to predict valid or invalid for each action independently. The problem is that it never sees the full picture. It scores each action in isolation, so it can't learn to distinguish between two actions that look almost identical but have opposite physical outcomes. That's the gap this paper targets. So let's see the related work. Prior work like React and Reflection are great at reasoning, but neither checks whether an action is physically possible before trying it. Swift Sage gets strong task scores but still executes invalid actions. Saycan does feasibility check, but it requires expensive RL training in the target environment. CWM fills a specific gap, step level offline and no RL needed. So the proposed solution here is a contrastive world model or CWM. CWM's core idea is to reframe action scoring as a ranking problem instead of a classification problem. Rather than asking, is this action valid? It asks, is this action more valid than these other candidates at the same time? It uses info NC contrastive laws with hard mind negatives to push valid actions away from invalid ones in scoring space. The base model here is Quen 2.57 billion, fine-tuned efficiently using LoRa. So let's move on to the mathematical part and the problem formulation. Formally, we want a scoring function f theta that makes a state and an action and returns a number. Higher means more valid. The goal is simple. The score for a valid action must always be higher than for any invalid action, a minus. The score itself is the log likelihood of the action given the state prompt extracted from the LoRa adapted model. So here's the full training pipeline of CWM. On the left, you can see the science world logs are fed into a hard negative minor that categorize the failures into three types through the interaction logs. The silent failures where nothing happens, explicit rejections where the environment says no, and cross transplants where an action is valid somewhere else but wrong here. These gets bundled into a training batch. One gold action one gold action plus 16 hard negatives, and the LLM scorer is trained with info NC. The dashed box on the right is the SFT baseline. Same model, same data, just different laws. That's what CWM replaces. So let's move to the experimental setup. Two studies were run. Study one is an offline test, 605 carefully constructed hard negative pairs across three difficulty levels. Study two is a live simulation. The scorer runs inside an actual agent loop across multiple task episode. Four systems are compared. CWM, SFT, the base square model with no fine tuning, and random scoring as a lower bound. So let's go to the experiment one. Study one test 605 pairs across three categories of increasing difficulty. Rejection only is the easiest. The invalid action is something the environment explicitly refuses. Cross task is harder. The invalidation action is valid in different tasks, and minimal edit is the hardest. One word changes like the like heat the water becoming cool the water. Physically opposite, syntactically, all but syntactically it is almost identical. So let's see the results of the experiment one. Look at the minimal edit column. This is the key result. CWM hits 93.2 precision at one. SFT gets 86.5 SFT gets 86.5 precision. That's 6.76% percentage point gap. And notice vanilla LLM scores 48.68%, 48.6%, which is actually below random at 59.5. The untuned model is actively misled by surface similarity. On rejection only, both CWM and SFT tie at 97.8%. Contrastive training only helps when negatives are physically close to correct actions. So let's move on to the experiment two. So the setup of this study to ask if we use a collaborative word model as live filter during task execution. Does the correct action survive the pruning? The key metric is GAR at K. GAR is golden action retention rate. If the gold action is in the top K candidates, it survives. We run in domain task the model was trained on, and other tasks it has never seen. Thermometer, chemistry mix, measuring melting points, and stuff. So let's move on to the results of the experiment too. In domain, GAR at 10 is 60%, meaning if you keep only the top 10 candidates in the correct action, survive 6 out of 10 times. That's an 18 to 90% reduction in the action space. Now under OD, retention rates are almost identical between CWM and SFT. But look at the safety margin. CWM is minus 2.39, SFT is minus 3.96. The biggest negative number means SFT's gold action is being pushed much further down the rankings under stress. CWM degrades more gracefully. So here's a discussion and analysis. Three insights from the discussion. First, CWM only beats SFT hard negatives. Easy ones are tie. That tells you info and C's values specifically in narrow decision boundaries. Second, SFT has a larger raw score gap than CWM, yet lower accuracy. That's because miscalibration. Big gaps don't mean correct rankings. Third, for system designers, this means SFT will specifically like SFT will fail specifically when two physically opposite actions look the same on the surface. CWM reduces the failure mode by 6.76 points to the hardest category. So let us look at the future world on collaborative world model and like what influence does the author on this make. Two integration paths are planned. First, plug CWM into DRR and reinforcement learning agent. CWM prunes the RL policy chooses among survivors. The expected benefit is roughly 80% reduction in the RL search space based on GAD at 10. Second, use CWM as pre-filter for react-shell agents. Remove physically impossible options before the LLM even starts reasoning. The paper expects 30 to 40% fewer invalid actions, especially on chemistry and thermodynamics tasks. Thank you for taking the time and looking at my presentation. Thank you so much.